Swayam Prabha, free DTH channel for education.
Greetings. In our previous lecture, we figured out how Alice succeeds in teleporting quantum of information. She had a qubit in a state of superposition represented by a point on the block sphere. This is the superposition state in possession with Alice. And she succeeded in teleporting this information to remote Bob, but they began with a certain resource. They started out with two other qubits, which were in a Bell state. Qubit number 2 and qubit number 3, which were in a Bell state, and they used that. And then subsequently, Alice also used a classical channel to communicate some information. So we're going to do the same thing now, but we will with a slight difference. And I will explain to you what this difference is. And it is important for the sake of generality so that we know that teleportation was achieved not because of any particular choice that Alice made in entangling qubit 1 and qubit 2. She could have made some other choice and teleportation can still be achieved. So that's what we are going to figure out in today's class. So qubit number 2 and qubit number 3 are two other qubits which are in our story. And they are in a state of entanglement. And previously, Alice entangled qubit 1 and qubit 2 in Bell state number 4, which is the superposition of 0, 1 and 1, 0 with a minus sign in between. However, the case that we are going to discuss now, we are going to ask, what if Alice entangles qubit 1 and qubit 2 in Bell state number 3? Bell state number 3 is the same superposition of 0, 1 and 1, 0, the anti-parallel spins, however, with a plus sign and not the minus sign. Does it make any difference to our story? And of course it does, but teleportation can still be achieved, and that's what we are going to figure out now. So Alice has qubits 1 and 2 in her possession. Bob has gone away to a remote location with qubit number 3, and Bob needs to figure out which is the original superposition state of qubit number 1, which is with Alice. But Alice now also has qubit number 2, which she can work with, and she can do some experiments to correlate qubit 1 and qubit 2. And this time she chooses to entangle them in qubit in Bell state number 3, j equal to 3. This is one of the 4 Bell states, and Bob really doesn't know in which Bell state Alice is an entangled 1 and 2. That is a piece of information which will have to be added to this communication challenge. So here, this is what we found earlier, which is the component of the 3 qubit vector in the Bell state number 4. Now we have to find the component of the 3 qubit vector in Bell state number 3. So this is what we have to find, and we can find it quite easily because this is the product vector of the 3 qubits, of which 2 and 3 are in a Bell state. They are entangled. You cannot factor them. But this Bell state is multiplied by an independent factor, which is the original quantum of information which Alice has to communicate, which is in qubit number 1. So the qubit number 1 multiplies the Bell state of 2 and 3, which is this. And now the Bell state in which Alice would entangle qubit 1 and qubit 2 is Bell state number 3, which is a superposition of anti-parallel spins, but with a plus sign. Earlier in our previous class, we considered superposition of anti-parallel spins, but with a minus sign. So now we can see that you need these two are anti-parallel. These two are also anti-parallel, but for the other reason. Here, Alice has qubit 1 is up and qubit 2 is down. Here, qubit 1 is down and qubit 2 is up. So you have that combination. And these are the two terms which will give you non-zero probability amplitude of finding the 3-qubit state in Bell state number 3. So these two terms will give you non-zero components, but you have to be careful because the corresponding probability amplitudes are scaled by this factor A0 with a minus sign, and this one is going to be scaled by A1 with a plus sign. So we have to keep track of these signs carefully and figure out what will be the contribution of this vector 3-qubit vector, which has got 4 terms, 2 of which will give you non-zero component in the Bell state number 3, in which Alice has entangled qubit 1 and qubit 2. But Bob does not know that Alice has chosen this particular Bell state to entangle 1 and 2. So that's a piece of information which will eventually have to be added. So let us see how this works out. So these are the two terms. The first term is this, and you have to keep track of the sign because there is a minus sign here. So this term, because of this minus A0 over here, will give you A0 along with a minus sign here. And notice that qubit number 3, which is with Bob, is in the state 0. Okay. So the term which gives you minus A0 gives the state of qubit number 3, which is in possession with Bob, and it is in the state 0. The other term which we must examine is this. And this one has got a plus sign over here. The Bell state has a plus sign over here. You have to remember that also, because this has got 1 0 here. This Bell state also has 1 0. So obviously you will get a non-zero probability amplitude, which will be proportional to A0. And you must keep track of the sign. So you have a plus sign here and a plus sign here. So that gives you plus A1 for this probability amplitude, but it also gives you some information about the state of qubit number 3, because for this particular term, qubit number 3, which is with Bob at a remote location, is in the state 1. So now you have everything that you really need to know, because now you know the state of qubit number 3. And what is that state? That state is a superposition of 0 scaled by minus A0 coming from the first of the two terms that we considered. And it also has 1 scaled by a factor A1 coming from the second term. But be careful, this time these two have opposite signs, whereas in the previous example, both of them had the same sign. And now we know the state of superposition of qubit number 3. It is A0, 0 minus A1, 1. Now this is not the qubit 1, which is what we call as chi, which is the original qubit whose information was to be teleported. So Bob doesn't have it. What is the difference? The difference is in the sign here, because you have with Bob qubit number 3, which is a superposition of 0 and 1, which is the quantum of information which Alice wanted to teleport, which is a superposition of 0 and 1, but 0 was scaled by A0, and this 0 is also scaled by A0, so that part is good. But this factor, this state was scaled by plus A1, whereas the qubit number 3 has got the vector 1 scaled by minus A1. So this is not the same state as chi, it is chi prime. So Bob still doesn't have the same information as we wanted to teleport. This is the original piece of quantum information. This is the one to be teleported. Bob has a qubit which is in the state of superposition, which is different. It is in a state chi prime. And the difference is because of the sign. And Bob must now do something to get the quantum of information which Alice would have wanted to teleport. So Alice must inform Bob as to which particular qubit Bell state has she entangled qubit 1 and qubit 2. She must inform Bob that this time she has not entangled them in Bell state number 4. Rather, she has entangled 1 and 2 in Bell state number 3. And that means that there is going to be a phase change over here. Now, having received this information, Bob can now do some experiment with his qubit, which is qubit number 3. And what Bob needs to do is to rotate his qubit about the z-axis through pi, because there is a change of sign, and it is a rotation about the z-axis which is now necessary to find what would be the original qubit 1 which Alice wanted to teleport. So he needs to do some experiment on that. And we have discussed these methods which are based on magnetic resonance spectroscopy in some of the earlier lectures. They are available at these links, which you may visit again as to how these experiments are done, how magnetic resonance spectroscopy is used. And with that information, which is there in these lectures, you can see that Bob must implement the Pauli Z gate, and he can do this using magnetic fields. So he uses a magnetic interaction between the qubit, which has a magnetic moment coming from the spin and an applied field, and rotate the Bloch sphere through pi to get the corresponding Bell state. Okay, to get the corresponding qubit state for his qubit number 3. So he's going to rotate the Bloch sphere through 180 degrees about the z-axis. So he uses the Pauli Z gate, which we have discussed earlier. This is the Pauli Z gate matrix. Notice that it is this which enables him to change the phase, which is why it is also called as a phase shift gate. So from the combination 1, 1, he goes to 1 minus 1 type of combination, right? So this is the rotation of the Bloch sphere about the z-axis through pi. And what happens is that if this axis is x-axis is seen to be considered toward you, when you rotate the sphere through 180 degrees about the z-axis, this x-axis will be pointing away from you. And the azimuthal angle is measured with respect to the half zx plane. So it is because of this half zx plane that the phase changes through pi. So now Bob has to do this experiment, and he will use magnetic fields for that. He will carry out a unitary transformation which will impact the time evolution operator, and his quantum system is in a state of magnetic field which will resolve the degeneracy. It will break the symmetry of the Hamiltonian, as a result of which the degenerate levels split into two, one for up and the other for down. So there is an energy splitting over here, which is plus or minus EH cross twice MC times the value of the magnetic field, which is used to break the degeneracy. It is a perturbation that he applies. And with this perturbation, which is minus gamma S dot B, that he breaks the degeneracy. And then the time evolution operator, which governs the dynamics of the quantum system. All right, and these details, again, I would like to refer you to some of these lectures which are available from our previous lessons on this topic. And the Schrdinger equation, the time-dependent Schrdinger equation, which is I cross del psi by del t equal to h psi, and the term in which we are interested now is this mu dot b term with the spin part, because we are now focusing our attention only on the electron spin. There can be other sources of angular momentum and magnetic moment, but we are not referring to those at this point. Our focus is on the spin angular momentum coming from the SU2. So this is the representation of the SZ operator. This is coming from the Pauli sigma Z. Okay. So this is the operator which is going to function in our analysis. This is coming. So your Z axis is considered to be in the direction of the magnetic field. So mu dot B becomes, there is a Bohr magneton over here, which takes care of all the proportionalities and the constants. And then essentially you have this SZ, but SZ is this 2 by 2 Pauli Z matrix, scaled of course by H cross over 2. So now your Schrdinger equation, really, our focus is on this term alone. So let us look at this. So I put the sigma Z operator over here. And with this, we can see that the time evolution operator, which is minus e to the minus I over h cross ht, becomes this. And it's a matter of simple substitution to figure out that there is this Larmor frequency which will determine the rate at which the system will evolve. And both the state 0 and 1 will have this term. So you have the Larmor frequency, which is gamma B0. This is the Larmor precision as we call it. And the time evolution operator, which has the sigma Z sitting in it, which is the Pauli Z matrix, will go as e to the I omega L by 2 and e to the minus I omega L by 2. And these two terms are, of course, are 0. So this is a combination of cosine and sine terms. So is this, but this one is with a plus sign and this is with a minus sign. So let us look at this further. So this is the energy splitting, and between the two levels, between the levels 0 and 1, they are now that degeneracy is removed, and you can write the qubit as a superposition of up and down, the downscale by the dynamical phase, which has the energy of this state, and the dynamical phase associated with spin up is the energy in the dynamical phase E0 is coming from the energy of this term. And you can certainly factor out one of these as common. You can ignore it because it can always be absorbed in a common phase and the normalization and so on, and it really doesn't matter. And it is the difference which comes over here, which will contain the Larmor frequency. But remember, this is even minus E0, whereas Larmor frequency is E0 minus E1. So there is a sign that you have to keep track of. And with that sign, you can see that the superposition is time dependent. It changes with time. At time t equal to 0, it is 1 over root 2 up plus 1 over root 2 down. But then as time changes, the mix of this is different because that point now travels in a plane which is parallel to the xy plane about the z-axis as time progresses. That is because of this dynamical phase, which is controlled by the Larmor frequency. And at time t equal to 0, this phase is obviously 0, but you wanted to change the phase of the down by pi, and you will achieve that phase after a time t, which is pi divided by omega L. So Bob can do this experiment and allow the phase to change from the qubit that he has. He wants to let it change till the phase changes by pi 180 degrees. So he can apply this magnetic field for a time interval which is exactly pi over omega L and switch it off. And now Bob will have his qubit, which was, if it was in the original state over here, then it goes to a point which is obtained by rotating the Bloch sphere through pi. So the phase changes. This from here, it is a plus combination. At this point, it is with a minus combination. And this is the operation. This is the experiment that Bob can do in his own very sophisticated laboratory, wherever else he is in the universe and whatever galaxy he may be in. He does have a magnetic resonance laboratory. He has magnetic fields. He has got clocks, and he can figure out what would have been the original quantum of information that Alice had. This is not cloning. Bob has the quantum of information which Alice had, but not anymore what Alice has, because qubit 1 is now in a state which is different. It has got entangled with qubit 2. So this is not cloning. Alice has had to inform Bob, remember, that she has entangled qubit 1 and qubit 2 in Bell state number 3. And without this information, Bob could not have obtained this particular result. And therefore, the limits of the special theory of relativity in transport of information are not compromised. So there is no difficulty with that. But entanglement has been used because Alice is able to do something to qubit 2, which impacts qubit 3 through entanglement. So teleportation has been achieved, but after some ancillary operations, some extra operations with that teleportation has certainly been achieved. Qubit is teleported using classical channels because Alice has to inform Bob. And how does she inform? She sends an email or she makes a phone call. She flashes light, laser light, whatever. And that information does not travel at a speed faster than the speed of light. So these ancillary channels were used, classical channels were used, but teleportation has been achieved. So thank you all very much. Essentially, we find that the selection of the qubit in which Alice entangles qubit 1 and 2. In the previous example, it was a Bell state number 4. This time it was Bell state number 3. And we can do this, we can have this kind of discussion even with qubit number 1 and 2. But now you know the methodology, that which particular qubit, which particular Bell state in which Alice entangles 1 and 2 is not important, because a corresponding experiment can be done by Bob to get the original quantum of information. But what is important is that Alice will have to use a classical channel to tell Bob, to let Bob know that she has entangled qubit 1 and 2 in a particular Bell state, which is one of the 4 different Bell states. So thank you all very much, and goodbye for now.